Okay, so we stopped off at the false discovery rate on the last video. Notice what we're going to do with the false discovery rate. Instead of looking for at least one false rejection of the null hypothesis, we're going to look at the proportion of false rejections out of total. So if you flip back to that table on maybe 3-4 slides back, C plus D is the total number of rejections of the null hypothesis. Let me just show you that. So see, if our decision is to reject, that's C plus D. So C plus D gives us our total number of rejections. Now, we don't know what proportion of those are true, correct rejections, or false rejections, of course. But we can make a fraction, which we'll call F, summarizing that proportion. And now, this would be 0 in the special case that we have no rejections of the null hypothesis, because it's possible that we have a bunch of tests, we never reject the null hypothesis. That can happen. So this is the false discovery fraction, this quantity F. It's a fraction of rejections that are incorrect, that are false. So controlling the FDR is making sure that the expectation of this fraction is smaller than epsilon. Now, some people like to control the false discovery proportion. We're not going to talk about that. Years ago, early 90s, the FDR, the false discovery rate, kind of gained precedence. I personally like the false discovery proportion. I think it has some good intuitive appeal that the false discovery rate does not have. But, sticking with majority opinion here, I think we'll just talk about false discovery rate, which is the expectation rather than the probability of this fraction exceeding a certain level. Okay? So we're going to control that at epsilon. Notice that the more correct rejections that we make, the more false rejections FDR lets you make. That's really important. So let me repeat that. Note that the more correct rejections you make, so the bigger D gets, the more false rejections FDR lets you make. Because the bigger D gets, the more wiggle room you get for C, right? While controlling that to be less than epsilon, the expectation of that. So this is a more lenient criteria than what we had discussed, because it's not saying we don't want C to be 0. C can be a positive number. We can make a few false rejections. But if C gets too big relative to D, that's when we start getting into trouble. Okay, so this is in many ways a more moderate way. I consider this like a good screening procedure. If you have a lot of tests to make, you do FDR because you need a little wiggle room on C. You don't want to be too strict about missing some effects that may be important. But if you have a very small set of contrasts, then I'd use that more strict criterion here, the probability. We call this, by the way, family-wise error rate control, and this false discovery rate control. Okay. So finally, strong family-wise error rate control allows for that possibility that even some of your H-naughts are false, but differing from FDR, it cuts you no slack for making correct rejections. So it doesn't take into account that proportion, that C plus D in the denominator on the last slide. So it's basically saying we can reject any H-naught, provided H-naught I is true. And it's just saying we'll control this so our probability of having any C bigger than 0, or having C overall bigger than 0, is smaller than epsilon. So this is allowing that some of the H-naught I's are going to be false, but again, it's way more strict than FDR. So if we're going to form multiple comparison intervals, we just want to perform what we call simultaneous confidence interval estimation, so that the probability that one or more of these CIs fail to cover the true parameter is less than epsilon, or the probability that all CIs simultaneously cover their parameters is greater than 1 minus epsilon. I prefer this second notation. That's usually how I, like if I develop a new procedure, this is how I'll state its efficacy rate. I'll say we were shooting for 95% coverage. I got 96% for this, 97% for that. You know, we try to get it as close to 95% as possible, but due to sampling error and other issues of performance, it's hopefully just going to be close, but a little above that. The coverage rate of your interval is going to be, like I said, typically a little bit larger than 1 minus epsilon, sometimes a lot larger though, okay? In effect, simultaneous confidence intervals, this is strong family-wise error rate is what we're referring to, only requires simultaneous confidence intervals for null values. So this actually requires more than strong family-wise error rate here. So we've talked about error rates from the weakest approach, which is per comparison, just controlling the per comparison, to the strongest, which is simultaneous confidence intervals. If a procedure controls one rate, it also controls the weakest. So if we control our effects using simultaneous confidence intervals, it also controls family-wise, strong and family-wise, it also controls FDR, and it also controls per comparison. Okay, so there's a hierarchy that naturally occurs. So the stronger your type 1 error rate, the harder it is going to be to find differences. So that's why you may be thinking here, wondering, why don't we just always use simultaneous confidence intervals? And I'm a big proponent of simultaneous confidence intervals. I think it's a good way to state your final, very sure experimental results. However, you run the risk of missing true effects if you only use simultaneous confidence intervals. So I've, over the years, kind of come to believe in this hierarchy of multiple testing. You know, maybe at first I'll use a weaker approach. I'll narrow down my analysis further and further and further until I get to a more focused set of hypotheses. Then I'll use simultaneous interval estimators at the very last to present results that I have a high degree of confidence in. All right, so a few points. Make sure you understand if any of these don't make sense, go back and review, reread, or rewatch. Per comparison hardly cares about incorrect rejections in total. It just doesn't think about the existence of other comparisons. And we need to be thinking about how our rejection or failing to reject a null hypothesis affects what we should do on the others. Per experiment doesn't want you to make an incorrect rejection, but if you make one correct rejection, it doesn't care how many incorrect ones you make. Okay? So per experiment says we don't want any incorrect rejections, but if we do make one, it could be 100, and we don't account for the number. FGR gives you a little slack over the family-wise. Okay, for example, if you get 19 correct rejections, it gives you a little bit more wiggle room on that incorrect rejection. Strong family-wise error rate doesn't care how many correct rejections you make, it still just doesn't want you to make any. So it's a very strict criterion. And finally, simultaneous confidence intervals not only pushes you to get the nulls right, but the non-nulls right. So it's at the top of the hierarchy here. So we'll go over this example in class. I want to make sure that you have enough background in this, and so I feel like this is worth some time in class. But we'll pick back up here in class and make sure that we've got enough knowledge and practical know-how to get through this example.